So we welcome you back to the next lecture. I'm Hasan, and I'll be talking to you now on observing with the CCDs, right? So what are CCDs? Yeah, CCDs are acronym for charged coupled devices. These are semiconductor chips, one face of which is sensitive to light, and generally they are in rectangular shapes, and they are subdivided into a grid of discrete rectangular areas, which are called the picture elements or pixels, each of about 10 to 30 microns across. And as time is progressing, these are getting smaller and more sophisticated. So here is a grid, and each one records the photons. The image here is not of any astronomical object, but of a human lung, right? And CCDs are used for imaging in a variety of things. We are more interested in seeing how it goes for astronomy. So there's this analogy where you can give the bucket analogy. You have a row of buckets, rows and columns of buckets. And as the rain falls, each bucket records a certain number of raindrops. It collects a little, some water, right? So here, these buckets can be thought of as these picture elements. These picture elements are sensitive to, they collect photons, and the raindrops are basically photons. So image of the sky, of any region of the sky comes. From certain areas, you would collect more. In certain areas, you will collect less, and some you will not collect any. And then there is a readout method. These get buckets in the first row, gets poured here, and it gets poured one by one into this beaker. And so you measure in each bucket how much of water has been collected, right? So first, this gets transferred here, these gets transferred, then this gets transferred here, amount gets flown here and here. So we collect how much was there in this one. And slowly we read out and give a count of how many photons were collected from each picture element. Here is a GIF image which shows the same thing. You have horizontal shift register, right? These are the photosensors. So as you see, that it's flowing into the, right? And it's one by one you will read out. So after you take a certain shot, a certain exposure, you cannot take another one immediately. There's a lag which is required, which depends on the CCD you are using. There's a readout time. This time when you expose it, and the time till it reads out the whole CCD is called the readout time. So you cannot take two exposures within this readout time. Here's a block diagram, cross-section of a CCD. And what you see is the CCD is sitting here. And it is sitting in a flask, the walls of which is a vacuum flask. There's a vacuum port here with which you create a vacuum. It's like a thermos flask. And there is a region where you fill in liquid nitrogen and you cool the whole thing. So the CCD, before observations for 5-6 hours or so, you cool it. Otherwise, the heat, the thermal photon will also leave an impression on the CCD chip. And the shutters are here. and the lens and the camera is here. So the image is taken, right? So you can imagine that this is a camera and it would image it and record it on this CCD. Let's not get into the details of this. This will be shared and you can read out. You have the copper flask and so on and so forth. This is basically to pour liquid nitrogen and cool the CCD. So these picture elements or pixels, CCDs come in various sizes, whether it's a 512 by 512, that is 26,000, 2,62,144 pixels, or it's a 4K by 4K, right? So this is the count of the pixels. And they are typically like 0.5 centimeters to 10 centimeters in linear size. Typical size of each pixels are 10 to 30 micron squares. And now the CCDs are getting larger and larger, 2 megapixels, 4 megapixels. So you have 4 million pixels or 2 million pixels. Basically, the pixel count increases the resolution and it increases the details we can get in a image. Yeah, the image becomes more and more clear. It gets more and more smoother and so on. Because in the small region, we are having many more pixel elements and we are collecting a more detailed image. So why go to CCDs? Initially, if you look into astronomy, initially people just observed, they saw with the naked eye, then times progressed and then they used telescopes and the eye, so they would see and record it, draw the images. If you see Herschel's and others, they used to see and record it. Then they got photographic plates. They used to put a photographic plate and record it. And as time progressed, the cameras improved and we went into the digital times and we have digital cameras, and these digital cameras are CCDs. So advantage of CCDs is that there are various things. The quantum efficiency is pretty high. Quantum efficiency essentially tells you the response of the detector. So for every 100 photons which are falling, how many will it record? And these graphs tell you that the CCDs have a tremendously high quantum efficiency. You have a curve which denotes the eye's quantum efficiency, right? Which is sitting in a specific wavelength. On the x-axis, you have the wavelength of radiation. So our eye can detect only within a certain wavelength, while the CCDs, as you see, these two curves are the bulk CCD and the thin CCD. They are ranging. They can record wavelengths right from almost 0.35325 all the way to 1 point, this extending much further up to almost 4-5 micrometers. And the efficiency also, it shows on the Y scale. The eye has not almost quantum efficiency 1, while those of the charge are almost reaching 97, 98 efficiency. So for every 100 photons, it can collect up to 97 photons. So efficiency is very high. And you have other also photo multiplier tubes, right? And but you can see that these CCDs have far superior to all others. Photographic plates also, as mentioned here, that also saturates after to a certain level. It is up to 1. And these are sensitive more in certain wavelengths, while charge coupled devices are sensitive. Then you have something called CCD gain and dynamic range. The gain of a CCD camera is the conversion between the number of electrons recorded by CCD and the number of digital units which a CCD contains. And this gain permits us to calculate the readout noise. It helps us to calculate what is the full well capacity, what is the maximum number of photons you can store in a certain pixel in a CCD. And it also gives you measurement of the maximum entropy of, right? And it is essential to handle the statistical part of your calculations, right? Where the images are converted into units of electrons, and you can do a lot of processing having this. Dynamic range is the response of the object, that is how faint light it can record to the brightest light it can record. So human eye also has a good dynamic range. In the times when there was no pandemic, you probably remember going to a movie theater. And if you go in late, initially you come in from bright sunlight and you are seeing things in bright sunlight. You go into the dark room and you don't see for a while, and after some time you can start seeing things around. So even eye has a big dynamic range. It can see, it can record in darkness and also in bright light. But the dynamic range of a CCD is much greater than that of the eye.
Sir,
yes.
Sir, are you talking about the signal to noise ratio? Means when the charge coupled devices captures a signal to noise ratio on a photography plate, and you can see the objects perfectly. Means like
yeah, exactly. And also recording recording very faint light to recording bright light, because our eye has a limit. Similarly, photographic plates have a limit, but CCDs have a very large range, the dynamic range. It can record very faint light as well as very bright light. Second, like for example, on the right hand side, I have written the CCDs can see much broader range of wavelength than human eye can see. You know, a silicon can record from 200 to 1200 nanometers, right? And CCDs, another advantage of that is the exposure. You can give very long exposure times, and hence you can capture even very still faint things. So even if the CCD has a limitation, but you are not exposing for 2 seconds, 2 minutes, 5 minutes, but rather for an hour or 10 hours and so on, right? While our eye can only record for a certain time, and then it refreshes again, right? You blink your eyes and it cannot record. So the exposure time durations can also be long, right?
Sometimes when you are finding that moving or the faint object in the TIFF image files, we are just trying to search the signal to noise ratios value of the objects which are having more than 5.0 or more than 4.5. Okay, sir. So is there a particular range that only from this certain value the object will be clearly visible in the signal to noise ratio?
Yeah. There are regions where the sensitivity is high, and there are limits to that. We'll come to that when we proceed ahead. Okay. So otherwise, it will get very technical now. Later, we can have sessions where we'll discuss this. Another important aspect of CCD is the linearity. If you expose to a certain light for a certain time, and you expose the same amount of light for double the time, it will collect double the amount of photons. And this relationship is linear. While this is not the same for photographic plates and other things, right? So this makes it very convenient for us to see that if an object is very faint and you need an exposure time of say 10 minutes to observe it, and right beside that there is another object which is bright, and it can be
Unable to hear you, sir.
Sir, you are muted. We can't hear you.
There is no audio.
I can't start my. I am logged in, Priya. Yeah, so I'm sorry there was a glitch in the internet. We had a shutdown. So um, we were talking about the linearity, and this response of a CCD is linear. So which means that for the same amount of light, if you expose it for X uh, minutes and you do it for 2X, it would collect double the amount and so on. So it's linear, and hence it makes it easier for do all kinds of digital work with these things. Noise sources in CCDs are various. You have the readout noise, you have the dark currents, you have the photon noise, and you have the pixel response. Each pixel's response may be not uniform. Right, so we'll look at this flat fielding. So very often to handle these problems of the CCD, each pixel may not have the right response. If you expose it to the same amount of light, a certain pixel may record more, the other may record less. And for that, there are certain processing things which we do with the images. You will not be required to do this for this particular workshop, what we are doing, because you would have processed images. But otherwise, if you take observations from some place, you may have to do this. Okay, so anyway, we'll talk about it. And what we have here is something called flat fielding. This is what is often where we expose the CCD to uniform light, either the twilight sky, where the sky just after the sun sets and the first stars don't appear, the sky has a very uniform, smooth thing. So you take multiple exposures with that, or you could, or you can have, or you may have a screen in the observatory which is illuminated very uniformly, and you take flat fields of that. And by doing that, you would see that when you are exposing it, in spite of exposing it to the same uniform screen, you are getting an image of this kind, right? There are certain dark patches, there are certain bright, yeah, half the CCD is bright, the other half is not, right? It's because of the pixel to pixel response may vary. Okay. Then the charge capacity of a CCD pixel has a limitation. And when a pixel is full with the charge, there's a certain amount it can store. And then when, suppose it collects more photons, you expose it to a brighter source and object, then it starts to leak into the adjacent pixels. And this process is known as blooming, right? So once the pixel element is full of the maximum capacity of photons it can have, then there is a spillage. It spills over to the adjacent ones. Okay. So this is again showing the blooming thing. And CCD's pixel is known as at full well, that is the maximum capacity which it has, which can store. And from observatory to observatory, the kind of CCDs they have, they may have different full wells. Like for the Kotamia Observatory, 65,000 electrons is the maximum which can have. So depending on what CCD is being used where, you have a limit of this. And to avoid this blooming, you have to take shorter exposures when you're exposing to a bright object, many short exposures, and add them up and use the linearity property of that, right? So these are examples of what happens when you have bright stars in the foreground. We are imaging this nebula, and when you have very bright foreground stars, then these pixels get overfull, and then they overflow, and you see these kind of bleeds, bloom stars images which you see, right? So you have to uh, take care of that. Then you have these dark columns where you are exposing it to a certain amount of light, but you are not registering anything here, right? So you have pixels which have these dark columns, and you have to uh, take care of all these things, right? Similarly, you have to look after the cosmic rays, bright columns, and hotspots. So certain uh, uh, regions can be excessively sensitive, and the hotspots are pixels with higher than normal dark currents, and their brightness increases linearly with this exposure time, right? So when we do cleaning, we have to, by using these flat planes, biases, and so on, we handle all these issues of this. And when there are certain pixels, by doing flat fielding, you also find out that certain pixels may be non-responsive. And to handle that, you can take the third image. You can take different images, just move it slightly so that the same object doesn't fall on the same bad pixel or so. And then you can recombine them. by shifting the images, because finally the image which you get is just a matrix of numbers, and it's just a digital image. And CCD images, if you realize, these are essentially black and white, but you can put different filters and you can construct a colored image by RGB combine and other thing, right? So you have biases, flat fields, and dark frames. And by dark frames, they show uh, by keeping your shutters closed, you take exposures, and you see that even when you are not exposing to light, you may record certain features there, and that would show the oversensitive ones, or those pixels which have not flushed out the things, uh, recordings in that,
Sir,
right?
what is dark current?
Dark is when you don't expose it to light, you keep your shutters closed, and suppose you are going to take a 5 minutes exposure without exposing it to that object. You keep the shutters closed, and you have the same amount of exposure, and you record something on your CCD. It could be the thermal background which you're observing, or it could be some dark current which is remaining on a CCD, right? So without exposing it to any light, if you are the image you get are these dark frames, okay? And then this when you're exposing it to a very uniform light, flat fields which we have seen, you can see there is some kind of a checkered region where you see certain brighter regions, though it's being exposed to the same amount of light, you are getting this kind of a pattern, right? And you can also see some dust spots which are sitting there on the CCD, right? So by taking these dark frames, that is by not keeping the shutters closed, you expose it. You take uh, you read out, or you expose it to a uniform light and see it, right? So these two things will help you clean up your images. And you have the science frames, you have these bias frames. From these two, you construct the science minus bias, right? Similarly, you have flat fields. Flat fields is an art which goes into it. And as you start doing observational astronomy and you go and record, you learn the techniques of what are the best ways of making these flats. Some people choose median, some people choose means of it, and so on. So you have flat minus bias, and then from sines divided by these minus bias, you get the final output image. So this will give you improved image of the whole thing, right? So with this, I will stop now. And as said, when we require CCDs in more detail, we'll do that. But as of now, you have to realize that CCDs are basically pixel arrayed pixels, right? And which basically records photons, and uh, you can, yeah, they are good because they have linear response. The dynamic range is good. Their quantum efficiency is high. They react very well to different wavelengths. You can, right? So this makes it a better device for imaging rather than photographic plates or photomultipliers and so on.
Sir,
Yeah.
sir, you told that you will just tell about the software which will be using for the HR diagrams, means how to install and how to use that software.
We'll be talking about it. Yeah. Yeah. Now we'll have a presentation by Priya, and then we will tell you what are the software which you'll be requiring for tomorrow. One which has already been posted, I think. You have to use TopCat. You have to install. APT photometric tool you have to install. And for both of these, you need to install Java first because both are Java applets. Anyway, we'll come to that. So now I'll hand over to Priya. Can you, okay. There are some questions. Yeah, dark currents we have discussed. The science image, the actual image we took with a CCD without any, that's right. These are the science images. These are the actual image which we take with the CCD without any process. I think Ahmed says, I think CCD now is also in most of electronic systems right now, like spectrometers. That's right. Okay, so now I will hand over to Priya.